At CERN's antimatter factory, unique facilities deliver low-energy antiprotons to several experiments that study antimatter properties from many different angles. One of these experiments, the Japanese-European collaboration ASACUSA, has just reported new precision measurements of the mass of the antiproton.
In this new experiment, we were able to determine that the antiproton mass and the proton mass are identical to more than 10 digits of precision. The special thing this time is that we've used a new technique to make the atoms very cold. We've achieved that by synthesizing the atoms in an apparatus which is cooled down to more than minus 270 degrees Celsius. What we're doing is we're synthesizing a special kind of atom which is half made of antimatter and half made of matter. This is called an antiprotonic helium atom. A normal atom is made out of a helium nucleus and 2 electrons orbiting around it. What we do is we replace one of the electrons with an antiproton. So our special atom has a normal helium nucleus, a normal electron, and a normal antiproton. We have a beam of antiprotons which are slowed down in this device, and then they are mixed with a sample of very cold helium atoms, a gas of helium which is inside this apparatus. And inside, these atoms are synthesized. We shine in on this atom a laser beam, and the laser beam reacts with the atom, and it makes the antiproton, which is orbiting around the helium nucleus, jump from one orbit to another orbit. This method that we developed is very, very efficient. We are able to cool down 2 billion antiprotonic helium atoms over a 3-year period.
With the upcoming Jelena, which is a new decelerator inside the Antiproton Decelerator, we hope to produce atoms with much higher number, and with new lasers we plan to increase the precision with the spectroscopy methods.
Pushing precision limits to compare the mass of the proton with the mass of the antiproton is a very important test of a key theory of physics called CPT, which is expected to be an exact symmetry for all physical phenomena. Even a very tiny breaking of this symmetry would provide a hint as to why the antimatter formed at the moment of the Big Bang seems to have disappeared.